Okay, so for this one again, we're going to use our Pascal's triangle in a way. Remembering that if I take the top two, I come down to the next row, I'm going up the bigger number, the top number goes up one, the bottom number goes to the bigger number. So let me say that again properly. So remember that if we take from the n minus 1th row, if we add, I always do it this way. If we add n minus 1, choose r minus 1, that term, to the n minus 1, choose r, we go to the next row, which is the nth, and the bigger one is the r. So equals n choose r, which looks like n choose n. That should be an r. There we go, n choose r. So we're going to use that here. Don't forget that, actually. I should have left it there, but anyway. All right, so we're going to let P of n represent our proposition, and let's decide why P of 1 is true. So is P of 1 true? It should be true. So prove that, you can see we'll have 1 choose 0 on the left-hand side, and 1 choose 0 is 1, and that's what we'll have on the right-hand side. So definitely true for P of 1. So we're going to assume it's true for P of k for some arbitrary integral k is greater or equal to 1. So what are we required to prove? And I should have written, let's just write our P of k so we've got it. So we're allowed to assume this one. There we go. All right, so what are we required to prove? We're required to prove that k plus 1, choose k, equals k plus 1. Ah, look, and we've got our assumption here, so we're allowed to use that, which is very handy. All right, so let's look at our left-hand side, which we can see is k plus 1, choose k. So remember, we're allowed to use this row here. This is our P of k, which starts the row above. So we're going to break this k plus 1 up into the two terms it comes from. So remember, comes from these k terms, if you can think about it, in the row above. So one of them is going to be choose k minus 1, and one of them is going to be choose k. All right, and that's just using our assumption there. All right, so now we can use our P of k, because we've got k minus 1 is k, and we are allowed to also assume that n choose n is 1, so k choose k would be 1. So this is using that's from our P of k. So again, that equals our right-hand side. This is a nice straightforward one. Therefore, P of k implies P of k plus 1. Therefore, P of n is true for our integral n is greater or equal to 1 by induction.